me begin. So we are discussing conformal field theory. And the key property of the conformal field theory that we started with is this one, that if you take a correlation function, the product of operators, assume that these are primary operators, so this correlation function evaluated at G mu nu as e to the 2 omega times some reference metric G0 mu nu is given by the following form. And then there is some anomaly function which we can ignore for most purposes. So what this gives us is a correlation function for a conformal field theory in a fixed background. Okay, but if the background metric takes the form of e to the 2 omega times G0 mu nu, omega is some arbitrary scalar function of x, then this can be related to the correlation function at G mu nu equal to G0 mu nu. Okay. These deltas are the conformal dimensions. And this is some known function of G0 and omega. Yes.
What is this factor e to the a?
This is some anomaly function, right? If you have a card metric, right, this doesn't depend on the x size, right? But this depends on the reference metric and the scale factor omega. But as I said, for most purposes, you can ignore this.
So the left side, why we are not putting prime, xi prime?
Okay, this is just rescaling of the metric, right? So xi prime comes when you make a general coordinate transformation, and then you combine the two to get.
Omega x ultimately will come from some coordinate
No. This is a general statement, right? Here, omega doesn't have to come from. So this is completely independent of coordinate transformation, right? This is a local while rescaling that we are doing. Just take the metric and multiply by e to the 2 omega x, right? Because the point is the conformal symmetry is more than general coordinate invariance, right? So this is a property of the conformal field theory, right? That is specific only to conformal field theories, not arbitrary quantum field theories. Right? And then there is general coordinate invariance, right, which I'll try to write down. Okay. So general coordinate invariance. Okay. So for now on, let's assume that y's are scalars. This is just for simplicity. We can easily generalize it as scalars. So if we make a general coordinate transformation under GCP, x mu goes to x prime mu, which is some function of x, the metric will change. We define g prime mu nu of x prime, dx prime mu dx prime mu equal to g mu nu dx mu. So this defines general coordinate. This defines g prime mu nu. And the statement of general coordinate invariance. So general coordinate invariance implies that if we calculate y of xi prime at g prime mu nu, that is the same as product over I y of xi at g mu nu. This is true independently of whether the theory theory is a conformal field theory or not, right? As long as you have background general coordinate invariance, right? This is always true, that you take a field theory, evaluate it matrix G mu nu, make a general coordinate transformation, and evaluate the new fields, a new correlation function at G prime mu nu. These two are the same, right? In particular for the scalars, right? This correlation function depends on the distances between the xi's, right? Say distance between x prime 1 minus x prime 2, x prime 1 minus x prime 3, and so on. Right? And the distances between x1 prime and x2 prime in matrix G prime is the same as the distance between x1 and x2 in the matrix G. Right? That's the way we relate G prime and G. Right? So it's clear that these two correlation functions should be the same, right? Because it's only a function of the distances between the physical distances.
Yeah, like if OIs are like tensors,
Yes.
then basically there will be some tensors function like dx prime by dx, and we'll see.
Exactly. There are some additional factors with which you multiply this if OIs are tensors. Is this clear? So these two are independent statements, right? This is a property of conformal field theory, not of any generic quantum field theory. This is a property of any quantum field theory, right? Assuming that you have defined it in a general coordinate invariant way. In particular, if the quantum field theory requires ultrafilament regulator, right? Say cutoff on some length, right? You will put the cutoff on the invariant length, right? The length that you calculate using this metric, appropriate metric. Then we said, so this is 1 and 2, now we are going to combine 1 and 2. Suppose we have a general coordinate transformation that takes eta mu nu to e to the 2 omega of x times eta mu nu. Look at 2 omega x prime. The general coordinate transformation is from x to x prime. Okay. So then this relation will tell us that product over I y of x prime I at G mu nu equal to 2 omega x prime times eta mu nu, because this is my new G prime mu nu, right? G prime mu nu is to by assumption that we have made a general coordinate transformation that takes eta mu nu to this. Simple example, Lorentz transformation, right? For Lorentz transformation, omega is just 0 because it takes eta mu nu to eta mu nu. Right? But the scaling, for example, will change. It will give some non-zero omega. So this is equal to product over I y of xi at G mu nu equal to eta mu nu. But if the theory also happens to be a conformal field theory, then you can now apply this relation over here. And we see that this is given by, this quantity is given by e to the minus sum over I delta I omega of xi. Well, this is prime, so omega of xi prime. Right? So now you can equate these two, and now this equality is between two correlation functions, both of which are evaluated in the flat matrix G mu nu equal to eta mu nu. So this tells us that product over I y x prime I and eta mu nu is equal to e to the power sum over I omega I x prime I times delta I
On the left hand side, the x's are without primes, no?
No, because this is not without prime, right? Because when I'm applying it here, right, the arguments don't change. So it's prime.
But the middle one is without primes. So
Yes,
why-
exactly. So I'm now equating this with this.
Oh,
See,
okay.
this was the identity earlier. Now I'm equating this with this,
Yeah.
right? And I've taken it to the other
The
side.
exponential has changed sign.
Yeah, exponential has changed sign, exactly. Is this clear? Then I could have written xi here and xi prime here. Then it will be plus. Okay. So let me repeat again that we define conformal field theory, okay, by saying that T mu mu must vanish. Okay, and vanishing of T mu mu get the identities that we wrote here. Then we said just as a consequence of general coordinate invariance, we have this identity. Then we combine the two, right, to write a relation that relates two correlation functions evaluated in the same metric. Right? Both general coordinate transformation as well as conformal transformation changes the metric. Right? We cancel them against each other. Right? And then we wrote a relation that gives the relation between two correlation functions of the same metric, but the arguments are changed by an appropriate coordinate transformation, right? But this is not an arbitrary coordinate transformation. These are those coordinate transformations under which the metric picks up a scale. Right? Lorentz invariance translation are trivial, where the scale, there is no scale in the metric. Metric is invariant. Right? Scaling is something under which metric does pick up a factor. Right? We will discuss scaling soon. And we also discussed last time spatial conformal transformation, right, under which the metric picks up a scale. Okay, so let's look at an example. Example: x prime I equal to lambda xi, or x prime mu equal to lambda x prime mu, take the x mu. Okay, this, and then every xi will transform that way. So in this case, g prime mu nu of x prime is lambda inverse times eta mu nu. So lambda to the minus 2 times eta mu nu if g mu nu of x is eta mu nu. Is that clear? Right? Because g prime mu nu dx prime mu should be invariant, right? So this lambda to the minus 2 will cancel against the lambda square that will come from there. So let's substitute it here. Right? That will tell us that product over I y of xi and eta mu nu is given by lambda to the power minus sum over I delta I product over I y of xi, y of lambda xi on this side. Yeah? Because I substitute for x prime I as lambda xi, and on this side is xi. And omega e to the omega is minus lambda inverse, right? From here. this point clear? Okay. Similarly, you can write down relations for spatial conformal transformation. And then of course translation and Lorentz invariance are already there. So using these, one can show that the form of the 2-point and 3-point functions of primary operators are completely fixed up to overall normalization constants. But let me just focus on the 2-point function and see how we can fix the 2-point function from this analysis. Let's consider O of x prime, 2-point function of two primaries. Okay. So this, before you do any conformal transformation or scale transformation, just from Lorentz invariance and translation invariance, you know that this should be some function of x minus x prime square. Right? It should depend on the difference, right? Because you can translate x and x prime by same amount, right? So it only can depend on the difference between x and x prime, and then it has to be Lorentz invariant. Right? So it should be a function of x plus x minus x prime square. Okay? So that's the only Lorentz invariant quantity that you can construct. And then you apply this. Okay? So O of lambda x. So if okay. So let's see what this tells us. Okay. So this tells us that if we replace x by lambda x, okay, that means if we write f of lambda square times x minus x prime square, this must be equal to lambda to the power minus delta I. So there are I runs over 1 and 2, right? Same operators, so delta plus delta. So lambda to the power minus 2 delta times f of x minus x prime square. That comes from this relation. Is that clear? Right? I just replaced x by lambda x on the left hand side. That gives the left hand side here, and on the right hand side, this remains as f, but you multiply by lambda to the minus 2 delta. And this fixes the form of f, right? Because this tells us that f of x minus x prime square is 1 over or some constant over x minus x prime square to the power delta.
One thing, sir, here x and x prime in the same coordinate frame.
Yes. So this prime is not the transform, right? Maybe I should say x tilde. If that's confusing. Yeah, x prime is not the transform of x. Okay, 2 points in space time, x and x prime, x and x tilde. So x and x tilde are like x1 and x2. Is this okay? Right? So you see the form of the 2-point function is completely fixed by conformal invariance.
So delta we already know.
Delta we already know, meaning it depends on O, right? So deltas characterize O, right? In a given conformal field theory, you have a set of primary operators, and their conformal weights are delta 1, delta 2, and so on.
But we know that independently. Like,
well, if you know the theory, you know that independently, right? So different theories have different deltas. Right? So in a given theory, we know what the deltas are.
Yes, that's the definition of the theory. Is that the
Well, you can define the theory by Lagrangian, right? Then given the Lagrangian, you can compute the deltas.
This property does not hold for every choice of operator, scalar operator.
No, this holds only for the primary operators, because this relation,
Yeah.
right, or the original relation that I wrote down, right, that holds only for the primary operators. right? Because that, if you remember that the way that this thing came is we said that under the conformal transformation, when you scale this metric, the different operators transform.
And they transform in a specific way.
Yeah, so the primary operators transform in a specific way, right? That's why they have this simple transformation. Right? But there are other operators we'll see later today, which are not primary, right? But they can be obtained from the primaries, right? So there is a neat classification of the operators in the conformal field theorem. So these are spatial operators, the primary operators.
So at this point, this is your definition of primary operators, those which transform as this.
Those which transform in the first, this thing that I wrote, right, under the scaling of the metric, those which pick up the to the minus delta I omega xi kind of factor, right, those are defined as the primary operators. Okay, again I am looking at scalars right now, right, but it can be generalized to general tensor operators.
Actually, I'm not understanding last line C by.
How do you get this? Oh, this is a property of the function. See, this function says that if you scale the argument by lambda square, the function scales by lambda to the minus 2 delta, right? Then the only solution is the power law, right? And that's this one, homogeneous function, right? So if you scale x and x tilde, replace x and x tilde by lambda x tilde, you pick up the lambda to the minus 2 delta because there is a 2 here. Okay, so now we are going to do some manipulation with this object, this two-point function. And this will also make it clear why the original definition in terms of the scaling of the metric is more useful than just this one. Right? I could have defined, so this is a property of the conformal field theory, right? That under a particular transformation that leaves eta mu to eta mu, right? The correlation functions transform this way. Right? But with the original definition, you can do much more, right? And we'll see an example now.
So the way we have figured out f here, this says that we could be figure it out for different O's also.
Yeah. So the point is you can easily check that if O and O, if it's O1 and O2, right? And if there's a different conformal dimensions, then C has to be 0. There is no way you can have different conformal dimensions, right, for O and O tilde, right? I mean, you require the full conformal invariance to show this, but this is something you can check. Right? But I have just simplified life to take by taking the same O's.
This derivation, it doesn't stop us this way. If we just had delta 1 and delta 2, it could just be lambda 2 or minus delta.
Yeah, you could have put a delta 1 plus delta 2 by 2. Right? I mean, just in this definition. But once you include also the spatial conformal invariance, then you can show that it's not possible to have this.
Sir, on the left hand side.
Yeah.
Yeah. On the right hand side, shouldn't there be lambda to the power minus 2 delta?
Here?
Yeah.
No, minus delta I, because that was the definition. The G, if G mu nu transforms to e to the 2 omega times G mu nu. Right? And then the transformation of the operator so as delta I times omega. Right? So that factor of 2 was already built in the way you define the conformal dimensions.
How far we can go to fix this correlation function exactly? Suppose if here
Up to 3 point, it's completely determined. Right?
which fix that conditions that only 3 point correlation function can be computed?
Well, basically the point is you can show that using the conformal invariance, right, of the conformal transformation, which includes the translation, Lorentz, and spatial conformal, right? Given any 3 points, you can take them to any particular 3 points that you want, right?
So we have
So that basically means that for the 3-point function there is no data, right? You can always bring it to any point that you want, right? So 0, 1, 2. So in that way you can show that up to 3 point you can fix. If you take the 4-point function, right, then naively you would have expected it to depend on, say, 4 times d space-time coordinates, but conformal invariance basically fixes 3D of them. Okay, now we'll do some manipulation with this. Okay. So x minus x tilde square is minus t minus t tilde square plus x minus x tilde square, right? Okay. So let's first make a weak rotation. Take p to I x naught, p tilde to I x naught tilde. Okay, so you get to Euclidean, d-dimensional Euclidean space instead of Minkowski space. Okay. And then in this O x tilde will be given by 1 over x0 minus x tilde 0 square plus x minus x tilde square to the power delta. Okay, and the metric is Euclidean metric. I equal to 1 to t minus 1. Right? I've just made a Euclidean notation, right? The standard procedure that we use in quantum field theory. So in the Euclidean quantum field theory, this will be the correlation function. This will be the 2-part function.
So you normalize just the O's by taking the C
So,
inside.
let me put the C in. You can do that, but I'm not. I mean that is not significant. Okay. Let's put the C. Okay, now we are going to use polar coordinates. So we introduce polar coordinate by the standard way. So x0 is rho cos theta 1, x1 is rho sin theta 1 cos theta 2, x2 is rho sin theta 1 sin theta 2 cos theta 1 and so on. Okay, the standard way we introduce polar coordinates in Euclidean space. So in this polar coordinates, the metric becomes d rho square plus rho square d omega d minus 1 square, where this is the metric on unit s d minus 1. Right? This is a unit d minus 1 dimensional square. Okay, it's like in 3 dimensions you have d rho square plus rho square times d theta square plus sin square theta d phi square, right? So that d theta square plus sin square theta d phi square is this d omega d minus 1 square. Yes.
We know x0 to the
It has to be real, then x0 has to be imaginary.
No. So you have made a Euclidean continuation, right? So now you are thinking of x0 as real. So t is imaginary. See, this quantity, right? Here t was real. I have not analytically continued t to imaginary values. Right? So x0 is real. Right? So this, we are now thinking of this as real coordinates, right? So if you take the conformal field theory in Euclidean space time, right, or Euclidean space, then the correlation function is given by this with all real coordinates.
But I think like that depends on like delta, right? Because there will be branch cut, and like you have to, when you do Euclidean continuation, this delta, if like it less than half or some kind of thing will happen, then it will be problematic to do that.
No, the point is normally what we do in any quantum field theory, right? You first define the correlation function in the Euclidean theory,
Okay.
and then you analytically continue, right? By weak rotation, right? So this is what to start with, and then you do analytic continuation.
Okay.
Right? In Hamiltonian formulation, of course, is different, but in the path integral, this is the way you calculate correlation function.
Right. Yeah. If you start from
Yeah.
here, yeah. Okay. Fine.
Right? And then you put the I epsilon prescription appropriately, right? So this, for example, has poles, and you have to say how to put the I epsilon prescription, right? And that you do that by starting with the Euclidean theory and then rotating the
Yeah, means I'm a little bit worried about this delta, because this delta, if it is a fraction, then there will be branch cuts.
Yeah, but the point is, as long as you don't, the branch cuts are on the real axis, right? Suppose you rotate t minus t tilde, right? As long as t minus t tilde remains complex, right? Between the imaginary axis and the real axis, first quadrant, there's no branch cut. Do it ever vanishes, right? So the branch cut will be on the real axis, right? So that's why you put I epsilon prescription. You don't go all the way to the real axis. You just stop epsilon before, right? And that's the way you define the analytic continuation. So even for any delta, this is fine, right? Because you don't really hit the singularity. Okay, this is clear. Okay. So you are going to write down this correlation function in polar coordinates. But of course, if we take general polar coordinates of x and x tilde, it's difficult. Okay. So you will use rotational invariance, okay, to choose some particular locations. Okay. So x, the first point, x, okay, we have full SOD rotation here, right? It's a d-dimensional quantum field theory, we have full SOD rotation. So using the SOD rotation, you can always take the first point x such that all the thetas are 0. Just like in 3 dimension, you can always put the first point on the z-axis, right?
Like translationally, you can make
By rotation, you can always do that, right? In 3 dimensions. So x will take to be at rho equal rho, and theta 1 equal to 0, theta 2 equal to 0, and so on. X tilde we put at say rho tilde, okay, some other point on the in the radial direction. Okay. But in general, we cannot also choose it on the same axis, right? If you have fixed origin. So we'll take this to be at non-zero theta 1, but rest we can take to be 0. Is that point clear? Right? So this means, okay, let's look at it from 3-dimensional perspective, right? You have 2 points to fix, right? By rotating the coordinate axis, the first point you put on the z-axis, and then by, you still have the rotation about the z-axis left, right? The second point we put on the xz plane, right? That's why the azimuthal coordinate phi, the analog of phi is 0, right? But theta is non-zero, the polar angle is non-zero, so I put it like this.
Can we not also use translation?
You can use translation, but you are not using it right now. Let's imagine that the origin is fixed. Okay, because see this point.
The function will
Yeah.
not have x dependent.
Yeah. Once you have written it this way, right? We have chosen a specific row, right? So let's not try to mess up with that. We keep the origin fixed. Now I mean, we'll see in a few minutes why we want to do it this way. That we don't want to mess up the origin, right? Because rho will play some special role. I mean, translation will not. This coordinate system is not manifestly invariant in translation, right? Because it requires a choice of origin. Okay. So now let's calculate x minus x tilde square. So x minus x tilde square is x0 minus x0 tilde square. So that's rho minus rho tilde cos theta tilde square plus 0 minus rho tilde sin theta tilde square. Is clear? So this you can expand it out. So rho square plus rho tilde square minus 2 rho tilde cos theta tilde. Okay. Theta tilde, the physical interpretation of theta tilde. That this is the geodesic separation on SD minus 1. See, imagine that you have one point here, another point here. Okay, this was the original x point, this was the x tilde point. Right? Theta tilde is this angle, right? So this angle has the interpretation that if we draw a unit sphere, let's imagine that we have drawn a unit sphere. Unit sphere. Then this theta tilde gives you the separation between the points where the units they are located on the unit sphere along the geodesic, along the great circle of the sphere. Okay, that's the interpretation of theta tilde. Okay, it will be useful to keep this in mind. So let's write this correlation function in this language. So this is given by C over rho square plus rho tilde square minus 2 rho tilde cos theta tilde to the power delta. So now we are going to make a change of coordinates. So let's make a change of coordinates, rho equal to e to the tau. So ds square becomes e to the 2 tau times d tau square plus d omega d minus 1 square. Right? This is a metric on R times SD minus 1. Okay? So because of the general coordinate invariance, That we have assumed that we are defining the theory in a general coordinate invariant way, right? What we can say is that if we take O of x tilde on R times SD minus 1,
We should be right.
yes,
In terms of tau and
yeah, you could have x and x tilde, you have to re-express in terms of tau and this, right? But that's understood. That what I mean by this is that I express in terms of tau and theta coordinates. Okay, we'll do that. I mean, we'll put this rho and O tilde in terms of tau. So what will it be?
is equal to the original one.
It will be equal to this,
to the power minus
but
tau.
yeah, we have to compensate because this metric is scaled by 2 tau, right? So this 2 tau, e to the 2 tau, we have to remove. See, if we take the metric, let me write this way. If we take the metric on R times SD minus 1 times e to the 2 tau, then it's exactly this. That's the general coordinate invariance, right? Because what we have landed up is in a space-time where we have the metric of R times SD minus 1 multiplied by e to the 2 tau, right? So let's write it that way first. So this is given by C over e to the 2 tau plus e to the 2 tau tilde minus 2 times e to the tau plus tau tilde cos theta tilde to the power delta. Right? Just general coordinate transformation, we have not done anything, right? We just reinterpreted that correlation function as correlation function in this transform coordinate system. But this implies now you use control invariance, use local while invariance, local scale invariance to say that OX tilde on R times S d minus 1 is given by C times e to the tau plus tau tilde, tau plus tau tilde and delta divided by to the power delta. Is this clear? Okay. So this is what I said earlier, that you see that thinking of conformal field theories as those invariant under the local scale symmetry is useful because you can do it in any space-time that you want, right? Not just in flat space-time. Here we have R times SD minus 1, there is a scaling of the metric, we just removed it by conformal invariance, by local while invariance.
So, we are scaling the metric by e to the power 2 tau.
Yes.
So, why is the factor of e to the power tau plus tau tilde coming in on the RHS?
Because you had this e to the some delta I omega of xi, right? So omega of x is e to the tau, and omega of x tilde is e to the tau tilde. Right? That's why you are getting tau plus tau tilde. Is this okay?
So, this tau coordinate is equivalent to time, or
We'll see. Right now, yes, I mean with some coordinate.
what is the equivalent to distance coordinate that we had in originally in x minus 6?
Which is the equivalent?
To the distance.
That's this
r.
one. This is x minus x tilde square, right? I'll just re-express in this tau theta coordinates.
This rho is the
Rho I may change variables to the tau.
tau.
Right? This is a change of coordinate system. Okay? So the invariant distance is still given by this.
When I'm using this polar coordinate system, then I had this rho, theta 1, theta 2, theta those things.
Yes.
But there is no time coordinate.
Because you are using Euclidean.
Okay, okay.
Right? Because right now there is no time coordinate because you have made everything Euclidean space. Right? So this is a relation between correlation function and the Euclidean. So I have derived what here a correlation function in the Euclidean space. Afterwards we'll go back to Minkowski signature. Right? Right now it's Euclidean signature. So that's why there is no time. So this can be simplified a little bit. Because you can take this inside, you can write this as C over e to the power tau minus tau tilde plus e to the power tau tilde minus tau minus cos theta tilde. I think somewhere a factor of 2, there is 2 here. This I can also write as C over 2 to the power delta and cos hyperbolic tau minus tau tilde minus cos theta tilde to the power delta. Okay? Okay, so this is a Euclidean result. Right? This is a Euclidean space. This is also Euclidean, right? All signatures are +1. Okay. But now I am going to again analytically continue to get a Lorentzian signature space, right? And that we will do by thinking of this as a Euclidean time. Right? So change tau to it. Okay? That t is not the same as original t. Okay, I could have used some different symbol, but let me use t. Okay? So change tau to it. So the metric now becomes minus dt square plus d omega d minus 1 square. See this, the scale factor you have already removed here, right? Because we by transformation. So the metric is just this from here, and the correlation function is some constant c prime over cos hyperbolic becomes cos okay? This is something you have seen before. The 2-point function in ADS that we calculated, right? When you took the boundary, right? When you took the 2-point function on the ADS and took the R to boundary, right? That had exactly this structure, right? So let me remind you what we had seen there. So if you take a scalar field in ADS,
So what is the
scalar field in ADS d plus 1, right? We took the limit r goes to infinity, r to the power delta plus delta, and then phi p tilde. Well, there we called it prime. I'm calling now this as t tilde. This was proportional to 1 over cos t minus t tilde minus cos alpha, right? Alpha was the geodesic separation on SD minus geodesic separation on SD minus 1, which is precisely theta tilde here to the power delta. And there, of course, delta was given in terms of the mass of the scalar field. So this was d by 2 plus square root d by 2 square plus m square r square. Okay, r was the radius and m was the mass of the scalar field.
So this correlation function is
proportionally-
calculated on the
Pardon? Sorry, yeah.
So this correlation function on the left side we have just calculated.
Yes.
It is done in the on the sphere, on the surface of the sphere, or
It's done in this space.
where is the r coordinate, the distance?
It's not there. Here also it's not there. Because you have taken the r goes to infinity limit.
Yeah, or
Right?
ADS case. But
ADS
here,
case.
I have not. I can't.
No, there's no r coordinate here. This is one less dimension, right? So that's the point, that ADS has one higher dimension than the CFD. Right? But that extra dimension, which is the r coordinate of ADS, right,
That has been fixed.
that disappears in the correlation functions, because we argued that the only sensible correlation functions that you can calculate in ADS are the ones that are near the boundary. Right? The interior correlation functions are not general coordinate invariant. Right? So you have to go towards the take the limit when the when r goes to infinity, and in that limit, with this appropriate scaling, right, this has no dependence on r. Right? And that's how to match with the CFT correlation functions.
Why do general coordinate transformations not change the structure of infinity?
Because the metric fluctuations are restricted to normalizable fluctuations which die off at infinity. Right? All fluctuating fields in ADS, right, are required to be normalizable. Right? And once you demand normalizable fluctuations, the metric automatically falls off to infinity. The fluctuating metric, part of the metric, falls off to 0 at infinity.
Can there be something like large case transformations?
We can make large gauge transforms, the metric still falls off at infinity. Right? You don't want to change the metric at infinity. Right? That's the definition of what we mean by quantum theory on ADS. Right? It means not just the metric, all fields are forced to have a boundary condition that makes them fall off at infinity.
So this is true for ADS at least ADS d greater than 2, right?
Yeah, for d equal to 2, there are some subtleties, but we can just ignore them for now. Yeah, they define those of quantizing in d equal to 2. Right? But certainly in higher dimensional ADS, you can just restrict only normalizable modes.
And the same thing can be said for flat space or.
Well, on flat space, yes, normally what you do is that you do path integral, right? You do integration by parts, right? Which is under the assumption that the fluctuating fields go to 0 at infinity. Right? So in that sense, you also implicitly assume this for flat space. Okay, so what we see from here is the first glimpse of ADS CFT correspondence, right? Some correspondence. Okay, so first of all, see that this space, right? What is this space? R times SD minus 1, right? Or this space, R times SD minus 1. This is the same as the metric on ADS at the boundary, right? If you recall the metric on ADS, right? There are of course complicated R dependent term, right? But for large R, right, up to an overall factor that is proportional to R, it was exactly minus dt square plus omega d minus 1 square. Right? If you look at the notes for ADS, right, global ADS metric that we wrote down, right? At large R, it exactly tau theta part exactly gives this. Right? So this is the sense in which one says that the ADS CFT correspondence relates the theory of quantum gravity in the bulk of ADS, okay, to a conformal field theory that lives on the boundary. Okay? because here the conformal field theory that we used here clearly lives on the space R times SD minus 1. Right? And this is also the metric on the boundary of ADS. Right? The correspondence between the operators in conformal field theory to the quantities in ADS are again in the limit when you go towards the boundary.
Just one thing, like in ADS, like here in CFT, this is a quantum theory, obviously, but in ADS space, when you computed the 2-point function, you just solve the like classical equation of motion. There is nothing quantum.
Well, it is quantum, because the way we define the correlation function, right, is really the 2-point function, quantum 2-point function, right?
Right, but while computing, we just use the classical equation of motion.
No, we use the creation and annihilation operators and put the creation and annihilation operators through each other, right?
Right.
So it's the quantum 2-point function. What you are thinking of is the other dictionary where you use what is called the differential dictionary, right? But in the Lorentzian version, right, we really computed the 2-point function, right? This calculation in ADS that we calculated, right? We thought of 5 as quantum fields in ADS, right, with normalizable modes, and then we just computed by putting the creation and annihilation operators to each other.
Sorry, so if you just compute the Green's function,
Yes,
and they then take one point to the
both points to the boundary.
yeah.
That's exactly what this is. This is the
That will be
Green's function.
classical, right?
Pardon?
But that is classical, right?
Well, I mean, you can say that's a classical computation, but it's actually a quantum result, right? Just like in flat space-time, right? If you have a free field in flat space-time, 2-point function, right? You can of course calculate by solving the Green's function. But you can also think of this as a vacuum expectation value of the time-ordered product of phi with phi, right? That's a completely quantum.
Yeah, because it is a free theory, so it's classical quantum, same thing. But like in the bulk, when you are computing, like there is gravitons or like gravity modes, background.
Yeah, so those you can take into account by thinking of the interactions, right?
Yes. Yeah.
And you calculate those by perturbation theory.
Right. But you are telling that when I take R going to infinity limit, those will not matter.
So those will matter. This is in the free limit. This is not exact result. Right? It so happens that conformal invariance fixes this. So it will be exact result up to normalization. Right? But the calculation that we describe is a quantum calculation in a free theory, right?
Okay.
And in principle, there you have to take into account interactions.
So yes, so let me make my statement. Like then basically the statement is that in ADS space, if I compute the correlation function take to the boundary by quantum correction or like by gravitons loop, whatever, that will only correct the constant in the coefficient, not the
For the
structure.
2-point function, but for high point function, it will correct the.
It will correct the
other
structure.
structure.
But for 2-point function only, it will fix the constant.
That's right.
Okay.
Right? Because this form
Mhm.
is dictated by conformal symmetry. Right? And the conformal symmetry is the symmetry of the quantum theory.
And for the higher point function, the delta will also get corrected.
Yes, for higher point function, everything can get corrected. Every delta will get corrected in general, right?
Okay, yeah.
By quantum corrections.
So you said delta we can calculate independently in this theory, in the flat space conformal field theory.
Yes.
Given the operator and the theory, we can know
Calculate
delta.
this.
And here we are comparing those two delta. So like
Yeah. So the point is you have to give a particular quantum gravity theory in ADS, right, for which you can calculate delta because you know the masses, for example. This is the formula, right? And that a particular quantum gravity theory in ADS should correspond to a particular conformal field theory in flat space.
these two are the same delta, but they
Well, only if you
correspond
choose
to
the theory
different
appropriately, right?
things. Yeah, they
The point is-
correspond to different things. This delta
Yes, exactly.
corresponds to
So, for example,
mass.
the most famous example is that the conformal field theory is n equal to 4 super Young mills, right? And the quantum gravity theory on ADS is type 2B string theory on ADS, right? So that's a very specific correspondence. So this is what you are seeing is the kinematics, right? How the correspondence works, right? But it's not that any theory of quantum gravity
Can
in
be-
ADS is equivalent to any theory of quantum gravity in any conformal field theory, right? A very specific pair are supposed to match, right? And the first thing you should check is that deltas match.
And this is only up to 2-point correlation function. What if higher?
Yeah, so everything has to match. So when you said there is an equivalence between these, right?
Yeah.
So all higher point functions should match.
And how do we do that?
Well,
So
we
that-
don't check it. So the point is what to do is that you make a conjecture and then you check many things, right? And whatever you check, you find that they agree, right? That's how you. So ADS CFT correspondence, for example, has not been proven, right? It has only been tested in many examples. Right? Then you calculate 100 correlators and you find that all of them match, right? And then you declare that, okay, we have got enough evidence that that conjecture is true.
Take this theory, quantum gravity in ADS, D-dimension. How do you know that there will be a CFT of this delta?
You don't know,
Okay.
or the vice versa, right? I mean, you can say, okay, you try to define the CFT correlators by starting with a quantum gravity in ADS and taking this limit, right? But there is, in general, there is an independent definition of the CFT, right? Only in special cases one can find both sides, right? You have a particular quantum gravity theory in ADS and a particular CFT, right? And only then you can say that you can test it, right? Otherwise, you can just use the quantum gravity theory in ADS to define CFT correlation functions and vice versa.
It is possible that there is no CFT with this delta.
Well, you define the CFT by saying that you start with ADS, quantum gravity in ADS, you calculate the correlation functions, take the boundary R goes to infinity limit, and you declare that that's the definition of the CFT correlation functions.
So it is guaranteed to have conformal invariance.
Yeah, it's guaranteed to have conformal because ADS, the symmetry of ADS is SOD, 2, the conformal symmetry of CFT is also SOD, 2, right? So it's guaranteed to have conformal invariance. Symmetries are the same.
I think it can also be shown that the isometries of ADS acts near the boundary as conformal transform.
That's right, exactly. Right? So maybe we'll see some of that later. How the ADS transformation, I mean, you know how the ADS, how the coordinates of ADS change under conformal transformation, right? Because we wrote down the conformal transformation in the embedding space. That's just the Lorentz transformation, SO2, 2. So using that, we know how it acts on the coordinates of ADS. Right? And when you go near the boundary, you can check that that transformation is exactly the way the conformal transformation acts on these coordinates.
Then the other way, that given a CFT, finding a quantum gravity might be difficult.
No, you define the quantum gravity as that.
Oh, with this.
The correlation function of the quantum gravity as that. Except that in that quantum gravity, you can only calculate boundary correlation functions.
Okay.
Right? There is no another bulk correlation function because you don't know in general how to continue into the bulk. Right? But those are not observable anyway, right? So you can declare that that's your quantum gravity. Right? But the important point is that when you have both sides, right, then you can make some non-trivial change, right? Other than just checking symmetries, right? Symmetries are the same, that you know.
So then what the error correcting code do? That construct the bulk Green's function starting from CFT?
The idea of error correcting code is to construct a bulk Green's function, at least in some approximate sense. Okay? That's what you'll see later.
So the left side you have not specified the theory. So suppose I have interacting problem. Then in that case, this correlation functions supposed to not match with the ABS correlation function.
No, it is supposed, if the correspondence is exact, it's supposed to match with the ADS correlation functions. Right? So this will correct, that will correct, but those should match.
This derivation independent of the theory, the Lagrangian of this CFT.
Well, delta can change,
Okay.
right? So they are also, because of the SOD, 2 symmetry, right? That structure you cannot change, right? Even though you got it by doing this complicated calculation of A dagger, right? The form of this correlation function, right, cannot be changed, right? Because it's fixed by SOD, 2 isometry. But M could get renormalized, for example, right?
M and delta will change according
Yeah, so if M changes, delta will change.
Here you showed that the 2-point function, like for ADS, thing. So CFT also fixes the 3-point function.
Yes.
So when we calculate, say in an arbitrary ADS, means not just free ADS. So there also the 3-point function.
Yeah, yes, symmetry. That's as long as it's fixed by symmetry, right? It has to be fixed because ADS has the same symmetries.
Okay. So there the coefficients will fix, like in ADS, what theory we have, or in the boundary CFT.
Exactly, yeah. So everything will be fixed, right? The things that are not fixed by symmetry, right? The conformal dimension, right, or the coefficients, right? Those are the ones that you have to match between the two theories, right? That's a non-trivial statement. That when you say there's an ADS CFT correspondence, that the deltas and the constants, right, that appear on the CFT calculation must be the same as the deltas and the constants that appear on the ADS calculation.
So their rescaling of R gives a R to the delta outside, 2 delta outside.
Yes.
That function, which is a dependence of T and theta. I mean, and SOD 2, D, 2 rotation in general can make R go to some function of T
Exactly.
theta R. How will this respond here? Like
Well, that's precisely that conformal factor that comes in omega.
E to the T 2 tau.
Exactly. That E to the not E to the 2 tau. Under a general conformal transformation, there is E to the 2 omega, right?
2 omega. Yeah.
So that 2 omega is coming because under a, here it's a coordinate transformation, right?
Yes.
But under a coordinate transformation, R can go into R into some function of theta
Yes.
and T, right? And that function of theta and T is precisely captures the omega. Because under a generic conformal transformation, right, omega is non-zero. Okay, so we at least see first glimpse of this correspondence that the operators of CFT, O T theta of CFT, are in some sense limit R goes to infinity. These are primary operators of phi T R theta. Okay, in the sense that the correlation functions of these
R to the power delta.
R to the delta. So the correlation functions of these will match the correlation functions of these. But we will soon see that not every primary of CFT is of this kind. Okay, but you have to just wait for a few minutes to see this. Let me just also add here is that if you take tensor fields on this side, the correspondingly you will get tensor operators on CFT. In particular, quantum gravity in ADS always has a metric.
Just one.
Yes.
Is it R to the power delta, R to the power minus delta?
I think R to the power delta because the correlation functions fall off as R to the minus delta, right? So you have to compensate by putting R to the delta.
But typically, if the field diverges near the boundary.
No, it's not diverging. It's because we are using normalizable modes, right? This is extrapolated externally. So when you use normalizable modes, it's actually falling off as R to the minus delta, right? And you have to compensate by R to the delta. I think you are thinking of this other way of defining correlation function as you put a non-normalizable boundary condition and then you differentiate, right? Yeah. So this is a slightly different way of defining, right? Which I mean, I think this Hardow's review calls it extrapolated externally, right? Instead of using differentiation. Okay, so now let me state another property of CFT, okay, that is the state operator correspondence.
What were you saying about the metric that there is a CFT operator?
Oh, I didn't say. I was going to say and then I yeah. So the metric, right? You can have a fluctuation of the metric around ADS, right? There is spin to fluctuation. The corresponding operator in the CFT is the energy momentum tensor. Okay, every CFT has to have an energy momentum tensor. Right? Every quantum field theory has an energy momentum tensor. Right? That is the operator that is dual to the metric fluctuation. Okay, and then if there are gauge fields on the on the ADS side, right, those gauge fields will correspond to some parameters, J mu, like kind of operator on the CFT, which may or may not exist depending on whether they exist or not depends on the particular ADS CFT correspondence that you are considering. But this one always exists. D mu nu always exists on the CFT side, G mu nu always exists on the ADS side, right? Because after all, it's supposed to be quantum gravity in ADS dual to a conformal field theory.
So some local symmetry in the bulk is becoming some
Global
symmetry.
exactly. So state operator correspondence basically says that there is a one-to-one correspondence between local operators in CFT with state in R cross SD minus 1. Okay, if you put the CFT in this background, y as it is square plus d omega d minus 1 square, right? Then it's like t is the time direction and the space part is a sphere. Right? You are putting the conformal field here on the sphere, right? And then the spectrum, the states in this theory are in one-to-one correspondence with the local operators and CFT. Okay, so let me just see how these are constructed.
So,
Yes.
in ADS, the correlation function was not coordinate, was not invariant under transformation, coordinate transformation, because we had a factor of r raised to delta.
Yes.
So if I make a coordinate transformation, when the operators in CFT, two different coordinates, the operators will be totally different in CFT.
No. What happens is the following. Let's take, so here, okay, we will not try to make general coordinate transformation. We will only make the isometric, right? SOD comma 2. Right? Suppose you start with this ADS metric and you make an SOD comma 2 transformation. Okay, which leaves the correlation function unchanged, right? Leaves the background metric unchanged and the correlation function unchanged. Or not correlation unchanged, is transform the correlation function but in a well-defined way. Okay? So the way, if it's scalar, for a scalar field the correlation function should remain unchanged. But R could change, right? And typically under an SOD comma 2 transformation, R goes to R times some function of theta and phi, so some function of t and theta. Okay. So as a result, what happens is that while this is invariant under SOD comma 2, right, this combination is not invariant, but it picks up a factor, t and theta dependent factor. Okay. And that factor is precisely the factor that comes in the under conformal transformation. Right? We say under conformal transformation there is e to the 2 omega, right? Or sorry, e to the delta omega. Right? That factor is exactly this, and that one can check. Okay? So that's why the SOD comma 2 transformation of this, right, is the same as the SOD comma 2 transformation of the correlation functions of O. Right? This you can check mathematically by simply comparing the way the two sets of correlation functions transform. That's a consistency check, that the symmetric transformation of these and these agree. Right? On this side, it picks up a non-trivial factor because it's you have to make a local while rescaling. Right? Because if you make a general coordinate, a conformal transformation, a coordinate transformation, right? The metric picks up some factor, and you have to remove it by the while rescaling, right? So the correlation functions pick up some additional factors. Right? On this side, right, phi is just a scalar. You are just making a coordinate transformation, so there is no rescaling anywhere, right? But because of this R to the delta, it induces a rescaling, right? And those two factors are exactly the same, right? And that's why the transformation laws of this and this match.
So for scalar operator and scalar phi, we have been able to correspond.
Yes.
So if I took something in CFT, some two rank tensor operator.
Like this.
Yeah, something like this.
Yes.
And try to find this. So I'll have to write the action for something which I'm guessing. Let's say I'm guessing that it's G mu, the corresponding T mu, and I'll write the action.
Well, you don't need to write the action to check the symmetric transformation properties. You don't need the action, right? You know how G mu transforms under coordinate transformation,
Yes.
right? It will not be invariant, but it picks up some definite factors, right? And you know how T mu transforms under conformal transformation.
But is that enough for me to say that they are the dual of each other?
No, that's the first thing you should check,
Okay.
right? And then, I mean, you have to check other properties.
For phi, we solved we took the action, we formed the differential equation, we saw that at the boundaries, we need to.
Yeah, but you can do the same thing here, right? Without knowing the details of the action, right?
Yeah.
Near the boundary, right? Basically the two derivative terms that dominate. That's the Einstein-Hilbert term. Okay? So you can study the form of the function near the boundary, and you can check that they match. That you have taken pickups, there will be analog of this R to the delta, right? and with the R2 delta, the two sides will match. Yeah, this you can check for every spin. This part is more or less kinematic analysis. Right? You don't really need the details of the action. Just free field.
Yeah. But we need to solve for a wave equation.
Yeah, but there's a free wave equation, right?
Yeah, free wave equation.
Yeah. So the non-trivial part is the interacting part of the Lagrangian, right? The free part is more or less trivial, right? It's the same in all theories. Right? That is more like kinematics.
Yeah.
Right? So the kinematic analysis tells us that the two sides transform in the same way. Right? The dynamical information comes in the interactions, right? Which starts affecting 2-point function and higher point function, or the details of the conformal weights, right? And that is not guaranteed, right? If you have not identified right theory with right theory, then the two sides will not match.
That is also not proven.
No, it's not proven. It's only tested, right? As I said, in ADS-CFT correspondence, we have tested it in many examples, but it has not been proven.
So far, we have assumed delta to be real and positive.
Yes, that basically follows from unitarity.
Right. I'm trying to.
Well, you have not assumed. We put some delta, right? Delta, you can see from here, right? That corresponds to some constant of the masses. If you want delta to be negative, imaginary, for example, or complex, then the masses will have to be negative, right? M square will have to be negative. Okay, so let me just say how this works. So the way we do this is the following, right? So let's go to the Euclidean space. Flat Euclidean space. Eta mu equal to just metric as not eta mu, delta mu. Just flat Euclidean space RT. And take a unit ball for this BD. A unit ball, it means a sphere, solid sphere of radius 1. At the origin, you put O, the local operator. Local operator is denoted by O. And the state in the CFT will be denoted by O. Okay, we have to see how, given O, how you construct the state. So what you do is that you define a path integral. Let's imagine that these are all the fields of the theory. These are the fields. E to the minus s CFT. Okay, some action. Okay, you don't need to know what action it is. Right? Some action for the CFT weight by e to the minus s CFT. O of 0. Okay, so you carry out path integral over the fields in the interior of the ball. And then you put the boundary condition that on the boundary of B. Well, I use maybe I should use a different symbol because this is not the same as the phi, the ADS. Not the same as the ADS. Chi equal to some chi 0 of theta. Okay, these are radial direction rho. So I am using this form of the metric ds square equal to d rho square plus rho square d omega t minus 1 square. So is this clear what we are doing? You are doing a path integral over the fields, right, with a O of 0 inserted, and the boundary condition that on the boundary chi is equal to chi 0 of theta. This will give a number. Right? If the path integral with some boundary condition, you get a number. That number, of course, will depend on what boundary condition you have put. Right? And it will also depend on what operator you have inserted.
Repeat the last part.
This integral will give a number, right? That number will depend on both the operator that you have inserted and the boundary condition that you have put.
What is 0?
Some function, given function, chi 0 of theta.
O of 0.
O of 0.
Oh, 0 is the origin. The 0 is the origin of the space. So this gives you what we call some FO of chi 0 theta. A functional of chi 0 theta, but the functional depends on what operator O you have chosen.
It is also depend on the location of this choice of O0, that argument of.
That's the origin.
Origin.
This is a ball, right? Unit sphere, right? And you have put the toward the origin, right? Is this clear? Okay. So a functional of the fields on S3, on SD minus 1. That's a state of the theory. You interpret this as a wave function of the state. In a quantum field theory, suppose you want to describe a state, right? In quantum mechanics, if you want to describe a state, right, if x is the basic variable, right, you specify it by saying that it's a function of x. In a quantum field theory, right, if you want to describe a state, you describe it by saying it's a functional of the field, but on a given time slice. Right? When you define a wave function, you don't define it as a function of x of t, right? You define a function of x, so at a given time slice. Okay. So here we are doing it at chi 0 of theta. So this is theta takes value on SD minus 1, right?
On the fixed radius.
Or the fixed radius is 1 here. You have fixed radius equal to 1. Okay. But this can be interpreted as a state in CFT on r times SD minus 1. R is the time coordinate, SD minus 1 is the space part. So let me repeat again. So this definition is a way to generate a functional on a unit sphere. And given a functional on the unit sphere, you can always reinterpret this as a particular wave function of the fields, and that describes some state in the Hilbert space, right? But the spatial direction is on a unit sphere. Right? That's important. This is a state in the theory, right? But this is a state when the spatial part is taking value on a unit sphere, right? Because this functional is a functional of something that takes value on a unit sphere.
And the state is at tau equal to 0.
You can think of the state as tau equal to 0, because rho equal to 1 will correspond to tau equal to 0, right? Because rho is equal to tau. So you call this O.
Have you used the factor into the CFT?
Well, you can define this kind of wave function, right? But for any field theory, right? But the various properties of the state that we will use, right? That requires that it's a CFT, right? Because this is now, otherwise you are doing this integral on RD, right? Whereas the CFT that you are talking about, the field theory is on R times SD minus 1, right? So you can go between the two by conformal transformation.
So, like in case of quantum field theory, in general quantum field theory, you saw that from RD you did some transformation to take it to a conformal factor times this R cross SD.
Yeah.
So the fact that we are writing it on R cross SD minus 1 uses the fact that
Exactly. Because the conformal factor, to be able to remove the conformal factor, you need conformal transform, conformal field theory.
And also the definition to work in both ways, like one needs to define a like time translation or dilatation operator of the states.
Yeah. So the point is, if you start on the other hand on R times SD minus 1, right? And say that suppose you are given a state there, right? And now you want to define a local operator, right? The way you will do it is you evolve it to tau equal to minus infinity, right? And then you make this transformation in the opposite direction. You go back to the Euclidean space, right? And tau equal to minus infinity gets mapped to a point, right? X equal to 0. Yeah, that's how you show that you can, starting from a state, you can also construct a local operator by going the opposite way. Okay, I'll leave it as an exercise to check that the Hamiltonian on this operator is basically delta on this operator. Okay, intuitively we can see it because, see, the Hamiltonian is tau translation, right? So tau translation is a scaling of rho, right? Because rho is e to the tau. Right? So tau goes to tau plus epsilon will scale rho. Right? And under the scaling of rho, this operator O will become a factor of something to the power delta. Right? And you can check that using that one can prove this.
So that state is an eigenstate of the field operator.
This state is an eigenstate of the Hamiltonian. It's not an eigenstate of the field operator. Right? This chi0 of theta is some function. Right? We define a state. Say any wave function, any functional will, so given a chi0 of theta we have a number, right? By this path integral. So that defines a functional of chi0 theta. Because a functional of chi0 theta means that given any function chi0 theta you should get a number. Right? So a functional, once you have a functional of chi0 theta, you can just interpret this as a wave function of something, some state. Just like any function of x. If you have a quantum mechanical system, right? Somebody gives you a function of x. You said, okay, now we have a wave function. Right? I can make the dictionary that function you interpret as a wave function. It will give some state. Right? So similarly, once you have gotten a functional of chi0 theta, right, you can interpret this as a state, as a wave function, right? And that's the state operator corresponds. That's the dictionary. That given an operator, how do you construct a state? This is the dictionary. Then you first construct this functional, and then interpret the functional as a wave function, right, which in turn describes a state. And then it's a little more work to show that that state that you construct this way is an eigenstate of the Hamiltonian with eigenvalue delta, where delta is the dimension of the primary operator. Yes.
What is known about the proof of this state operator correspondence in 2 dimensions and in higher dimensions?
I think, okay, it depends on how, what exactly, how rigorous you want the proof to be, right? But this idea, this is the one way of going that from operator to state. Yeah. And as I said, to go from state to operator, right, you start from the R times S3, or SD minus 1. You go to tau equal to minus infinity. Yeah. And that you can now do the conformal transformation in reverse direction to get a local operator. Right? So in that sense, this is constructive proof. That you can, given a state, you can construct an operator and vice versa.
Shubhpranil was saying something like there is no general proof in d greater than 2, but in d equals 2 there is some proof by I don't know, using methods of Riemann surfaces. Or
I think in d equal to 2 one can do more rigorous analysis, right? But this level of proof also works in higher dimension, right? Because it's just from this map between R3 times R times SD minus 1 to RD. So we'll assume this to be true and proceed. So then now I can state the second aspect of ADS CFT. And that is that there is an isomorphism .
isomorphism is this precisely.
Well, here I have not talked about ADS side. Right? ADS side you had discussed earlier. You just take the ADS and quantize the fields in ADS, subject to this normalizable boundary condition. You get a set of states, right? And those states are in one-to-one correspondence with the states of CFTD, right? And this in turn is isomorphic to local operators. Okay? So from that point of view, you can say there is an isomorphism between local operators in CFTD and the states in the Hilbert space of ADS D plus 1. Is this point clear? Okay. But this already introduces several puzzles which we'll discuss and then maybe we'll stop.
Which states are we talking about again? Operators in CFT of dimension D.
Okay. So the statement is between the isomorphism between Hilbert spaces. Hilbert spaces of CFT on this, right, is isomorphic to Hilbert space of quantum gravity plus matter on ADS D plus 1. The kind of Hilbert spaces that we built on the second lecture, right? So there you know what the Hilbert space structure is. I mean, at least you got some glimpse of Hilbert space structure by quantizing fields in ADS. Right? That spectrum is supposed to match the spectrum of CFTD on this. Right? But this in turn, by the state operator correspondence, right, corresponds to the spectrum of local operators in CFTD.
No, what is exactly the RHS then? States of quantum gravity and matter.
Yeah, on ADS D plus 1. Just like we quantize a scalar field in ADS, quantize the gravity in ADS.
So if we quantize gravity plus matter, what does it?
Just like we quantize phi, right?
Yeah.
In ADS and got the whole spectrum.
Yeah.
You can quantize G mu nu in ADS, get the spectrum.
And that Hilbert space should be equivalent to
The Hilbert space of CFT, right? After you take into account all the corrections, right? We quantize free scalar field, then there can be interaction terms, right? Which will modify the spectrum, which could modify the spectrum. After you take into account all that, right? That spectrum is supposed to be equivalent to the spectrum of CFT on R times SD minus 1. Right? In particular, type 2B on ADS 5 times S5, if you calculate the spectrum of that theory, right, by doing all this, first you do free field theory and then you take into account interactions, calculate corrections, that whole spectrum should match with the spectrum of CFT.
yeah, the operator is T meaning for this.
No, operator, CFT has many operators, many primaries, right? For each of those primaries there should be a state in CFT, right? And for each state in CFT there must be a state in ADS. Right? That's the isomorphism. Right?
Even for free quantum gravity,
Yes.
there will be a CFT and the
Mhm.
state between the Hilbert spaces there should be an isomorphism.
Yeah, exactly.
Sorry, but the other one, so for generic matter field, what is the guarantee that both is still a CFT?
Well, if it's ADS D plus 1, if we can define a consistent quantum gravity plus matter in ADS D plus 1, it has SOD comma 2 isometry, right? And that translates to conformal group on the boundary theory.
So these are matter which does not change the asymptotic.
Exactly, yeah. So the asymptotically it's still ADS. I mean, you quantize the theory by putting normalizable boundary conditions at infinity. Okay, so let me remind you what the spectrum that we got on the ADS side. So let's recall that for a single scalar field, phi dr theta in ADS D plus 1, we found many states, infinite number of states. Right? Vacuum. This is a vacuum. Then you have single particle states. A dagger, NLM the energy was delta plus L plus 2n, right? L plus 2n or L plus 2n, let me just check. Yeah, delta plus L plus 2n. Remember this, right? Then two particles state. A dagger N L M A dagger N prime L prime N prime on packing. Okay, so for this the energy would have been delta plus L plus 2n plus delta plus L prime plus 2n prime. So all these states must exist on the CFT side, right? If this is true, isomorphism, all these states must have the counterpart on the CFT side. And hence, all these states must have a local operator on the CFT side. For each of these states, we should be able to find a local operator. Right? So far, we have found only one, right? The limit of r goes to infinity, phi rt delta, right? So where are the others? Secondary. Well, not all of them are secondaries.
Phi square can be there also, right?
Phi square. Well, it's not clear that phi square defines a proper operator. Okay, let me do this. So first, the single particle state. The L equal to N equal to 0 is the primary. Okay. The others are the secondary. They are derivatives. So let me, phi these are derivatives along t theta direction. In other words, from the CFT perspective, right, they are the derivatives of the primary fields. These are the secondaries. Okay, these don't transform as primary. You can easily check that if phi transforms as a primary, its derivative doesn't transform as a primary. There are inhomogeneous terms in the transformation law. Just like in general coordinate invariance, yeah, the derivative of a tensor is not a tensor, right? So the same thing is true here.
So what is mu?
Yeah, so these mu1 to mu k are the indices which are along the tangential direction, right? On r times SD minus 1, not the derivative with respect to r.
D of them.
K of them, right? If you take k derivatives, then it has conformal dimension delta plus k. Okay, and that matches with this L plus 2n. Right, and of course here there are many states, right? L plus 2n, there are many states because m can take arbitrary value. L plus 2n together is fixed, but otherwise it can take arbitrary value. All of those are obtained by varying these mu's. Right? Different derivatives generate all these states. Is this clear? Now, what about two particle states? Here, things become confusing. And the point is that the fact that the two particle state has energy equal to sum of single particle states is not strictly true in ADS, right? That we have discussed already. Once you take into account interactions, right? Then it's like a bound state of two particles, right? There are some interaction energies which will contribute, right? So this relation is not exact. Okay? So similarly, we expect that in the CFT, right, there is no reason why there should be an exact conformal operator whose conformal dimension has this structure.
Certain approximation.
Yeah. So the point is, in this becomes exact in the large R limit, right? So not every CFT has such large R limit, right? So if there are, so the point is large R limit, right, which is called the near flat space limit, right? Those correspond to some special kind of CFTs, okay? And those special kinds of CFTs have the property that there are operators whose conformal dimensions are the sums of the conformal dimensions of other operators.
R is the radius of ADS.
R is the radius of ADS.
Sorry, but how does CFT sees the R?
CFT, there is a parameter in CFT which is the R, right? So for example, in particular, if you look at the example, let me use the example of okay, let me take this type 2B on ADS 5 times S5 is supposed to be dual to n equal to 4 super Young mills with gauge group SUN. Okay, we don't need to know details of what it is. It's some theory of Young mills group SUN and some matter content. Okay, so this is a CFT, this is a quantum gravity theory. Okay. So this has two parameters. One is the string coupling, which we'll call GS. Okay. The other one is the radius. On the Young mills side, again you have two parameters, G Young mills and N. N is the N of SUN.
So that cross S5 is not a sphere S5.
It's a sphere S5. No, but not the sphere. Yeah, it's an independent sphere. Because 2B is in 10 dimensions, right? So total dimension has to add up to 10. Okay, so there is relations between these two, right? I don't remember the exact relation. I think GS is G Young mill square, and R is something like G Young mill square n to 1/4 up to some, let me say, order, some proportionality constant. But the important point is that if you want to keep GS fixed and take R to infinity limit, large R limit, that on the Young mill side corresponds to keeping G Young mills fixed and then take n to infinity limit, right, in the large n limit. So if this correspondence is true, then I would expect that in the large n limit at least, the operators in the CFT should have the structure of this factorial structure where given a primary operator, you should be able to consider other primary operators whose dimensions are sum of dimensions of the original primary operators, right? There should be some primary operators or some set of operators which correspond to single particle states. Some other operators should correspond to two particle states. Some other operator corresponds to 3 particle state, and so on. Okay. And those are provided in the Young mill side, okay, by the number of traces that we take on the operator. Okay, so let me just give some rough example. So single particle state correspond to single trace operators. That's the trace of F mu nu, F rho sigma, etc., etc. One example, one trace only. 2 particle states should correspond to double trace operator. Trace of F mu nu, F rho sigma, etc. Trace F mu prime, F rho prime, sigma prime, etc., and so on. 3 particle state will correspond to triple trace operators, and so on.
Is there a way to see this, that single particle states will be single trace.
Well, you see it by looking at the details of the correspondence, right? A priori, you don't even know that a given conformal field theory corresponds to a large radius ADS, right? So only some special class of conformal field theory has this large radius limit, right? And and what characterizes those conformal field theories is this, that there should be a way to organize the primary operators in the conformal field theory, right, into the ones that are dual to single particle states, the ones that are dual to two particle states, and so on, right? It happens that in the case of n equal to 4 super Young mills, that's organized by traces, right? In another example, it may be organized by something else, right? But the generic word that one uses is single trace, right? Even though it may not have one may be able to find an example where it's not related to trace, right, but something else. Okay? But there should be something which organizes the operators into a single particle, two particle, three particle, etc. Right? And that requires special properties of the conformal field theory. Not every conformal field theory has that property.
So under n tends to infinity, how does that look like SUN?
SU infinity, meaning it.
What are
Yeah, so the point is there is a way to reorganize the perturbation theory of SUN, right, this Thieves limit, which tells you that you organize the perturbation theory as an expansion in G Young-Mills square times n. Right? Now, in the n goes to infinity limit, right, it becomes a strongly coupled theory, because G Young-Mills square n is the perturbation parameter, right? So you don't, it's hard to do calculation directly, right? But using supersymmetry, one can get some results, and those are the results one uses to make this conclusion that single trace operators are like single particle states, or two trace operators are like two particle states, and so on.
Sorry, maybe I missed it. Why did you say in the larger limit that on the ADS side that relation is like that?
Because in the larger limit, right, these two particle states can be have a large separation, and you can ignore the interaction, right? If you think of the ADS as a box, right, of size r, when r is small, then the things are close together, right, and you cannot really separate out very much.
But even then we want the correspondence to be true.
Well, no, in that case, these may have corrections which are of the same order as the original variable.
And there should be corresponding corrections on this side, no?
Exactly. So the point is, if you take this large n Young-Mills, right, and go to not infinite n but large but finite n, then you should start seeing that there are corrections, right? For example, the dimension of this operator, right, should be approximately equal to the dimension of this plus dimension of this, but then there can be corrections.
And those corrections should also be equivalent if there's
Exactly.
an isomorphism.
Yes. So those corrections should match the corrections that you calculate on this side. Yeah, and that has been tested to, very good accuracy. If people use this, basically what happens is that the computing corrections of these operators, right, you can organize by this thermodynamic Bethe ansatz, right? You map it to a spin chain and you can try to see this correspondence.
Generally in a CFT, there will be many primaries, so we have to add more scalars here.
We have to add.
More.
Yes, exactly. So when you say type 2 your ADS5 times S5, it already comes with its own field content, right? There is no ambiguity on how many scalars it has and how many vectors it has, right? It already has some very specific set of fields, right?
Okay.
Based on that, you compute the spectrum, and that spectrum is what you match with on this side.
Okay. Is this finite? This matter field content?
No, both sides have infinite number of fields.
Okay.
In n equal
Because
to 4 it's finite. In n equal to 4 number of fields are finite for fixed n.
For fixed n, yeah, but in the n goes to infinity limit, it's not finite, right? Number of primaries is finite, you are saying. Number of primaries.
Number of fundamental fields like in Axel Howard pyramid.
But that's not what is important here, right?
Right.
Because the correspondence that you are trying to make.
Yeah, otherwise it's infinity. Yeah.
Because the type 2b
you
side,
can multiply
right,
any trace.
you have the whole string state tower, right?
Right.
Which you don't normally count because they are heavy states, right? But the full theory has all these string states also.
So many massive states can be here. Correspondingly, there will be deltas.
Exactly, that's right. But what people normally check is supersymmetric states and which are close to supersymmetric, right? Because the point is that on this side, because the theory is strongly coupled, right, it's very hard to control this, right? And the only control that you can exercise is by using supersymmetry, right? So there are states on the on the CFT side which are either exactly supersymmetric, which are called BPA states, or nearly supersymmetric. Their spectrum you can calculate reliably, right? And that spectrum you try to compare with the other side.
So this fact that when we take this R to infinity, the radius to infinity, it will approximately at least give us one particle and two particles.
Mm.
So this can be done for all all CFTs or like all asymptotically ADS spaces.
No, because you can have asymptotical ADS space where R is small, right?
Yeah, right.
For those, this formula can get large corrections. Right? So in that case, the two particle state may have really no simple relation with single particle states.
But suppose I have an asymptotically ADS
Yes.
space. So there, if I take R to infinity, say,
No, R is a parameter of ADS, right? Capital R, right? So capital R is a parameter. It's not the distance from the center, right?
Yeah, that's true. Means I'm saying in the sense that where you can take the ADS radius to infinity to reach flat limit.
Yeah, if you can take, then the corresponding dual CFT must have this property that the states will be classified in that limit into the or the operators will be classified into the in that limit as operators that are dual to single particle states, operators that are dual to two particle states, and so on.
An example of such a theory where this can be done is will be large central charge CFTs, right?
Yeah, that's exactly n equal to 4 super Young mills has a large central charge limit. That's n goes to infinity limit.
I mean, theories that are not super Young-mills but has large central charges will also have large R.
That's not completely clear. That you can try to, we may be able to get large central charge without having large R, right? Because central charge, I mean, it is true that if you take the large R limit, right, then at the two derivative level, it corresponds to large central charge, right? But you may be able to achieve large central charge without taking large R limit, right? Because then the hard derivative corrections become important in the central charge computation, right? And those could become large for some other reason.
Sorry, I mean this large, I mean this flat space limit, so as you are taking this R to infinity, I mean you know that the asymptotic structure of flat space and
No, we are not taking R to infinity, taking the flat space limit, right? I was saying take the R goes to R large R limit, right? You keep the asymptotic structure exactly as it is. You can take R to be as large as you want, right? And as you take R to be larger and larger, okay, this formula becomes more and more exact. Right? That's all you are saying. And hence, from on the CFT side, if you take the corresponding limit, right, it must be that the CFT operators, operator dimensions, organize themselves into this structure. Right? There are some operators which you can identify as single particle states, and then other operators which you identify as two particle states, whose conformal weights will be sums, and so on.
And we are doing this for each scalar we can find.
Each scalar, each field, exactly.
And how is there a fixed number of fields in a given field?
No, there are
Type
infinite
2
number
by
of fields,
type 2
because
by-
string theory has infinite number of fields, right? But you have to organize them, so you don't want to check every one by one, right? You want to check as a whole family. Right? Okay, maybe I can just say one more thing, that there is one limit, okay, where even for finite R, there is a relation that you can test in CFT. Okay? And that is the following. Imagine that you have a finite radius ADS. Okay, so two particle states look highly interacting, you cannot do much with these two particle states, right? But what you can do is that even if it's finite radius, right, you can always go to R, smaller goes to infinity limit, right? Imagine that you have a state in which there are two particles, right, which are rotating about each other. Okay, and if you take the limit when the spin is very large, okay, then because of the centrifugal force, they are going to get pushed out very far away, right? And once they get pushed out very far away, right, because of large angular momentum, right, then their energies become almost equal to sum of the individual energies. Even though R is capital R is small, right? We are separating them out by giving them large spin. Is that clear? So in the large spin limit, okay, it says that the operators in conformal field theory must arrange themselves such that some operators you can take identify as single particle state, some other operators you can identify as two particle state, and so on. And their dimensions must satisfy this. That the two particle state operators have conformal dimension that is nearly equal to sum of the conformal dimensions of the single particle state. And the correction should follow as you take spin to larger and larger. And this property you can actually check even in the CFT directly. Okay. So if the CFT didn't have this property, then ADS CFT couldn't be right.
So spin is large as in wash is large.
The L, yeah. Okay, individual L's may be small, right? It's the orbital spin which is large. Okay, so imagine the two particle state, okay, which are rotating about each other with a very large spin. Okay, that state will have energy, right, equal to the sum of the energies of individual particles. Right? So that gives you a particular relation between the conformal weights of the operators in the CFT, in the large spin limit. Right? Irrespective of what the central charge is, whether the R is small or large, right? Irrespective of whether R is small or large, just in large spin limit, it implies some relation between the conformal weights. Right? And that you can independently verify in conformal field theory by using various bootstrap and so on.
Is this why taking a large spin limit in CFT makes sense? And what LD and
yeah, in a sense you can say the ADS justifies why large spin limit makes sense. Right? But on the other hand, you can within CFT itself you can justify, provide independent justification, right? But these two things match, right? The fact that the large spin limit makes sense follows from ADS, because in ADS by taking the large spin limit you should be able to get to almost independent object. The particles can remain almost independent, and you see its manifestation also in CFT.
Is there no other way to send the particles other than spin? Is there any other way to send the particles?
Well, you have to overcome the gravitational attraction, right, between the particles.
Yeah,
So
just having momentum in opposite direction will it not?
but momentum is not a good quantum number here, right? You need, if you push them out, right, they'll eventually come back, right? So the point is the particle, but if you make them rotate, right, then it's a stable situation, right? They are just rotating about each other's orbit. Right? So those states are well-defined states, and those are the ones that must have manifestation in CFT.
So for large spin, this interaction is small, or it is a
Effectively, the interaction becomes small, right?
comparatively small. That's the thing.
No, it goes as 1 over j. The larger you put j, right, the farther separated the particles are, right? There's a standard centrifugal force, right? The more centrifugal force you have, the farther out there, and hence the interaction between the particles becomes small.
So is the dynamics of the two states also similar? Like
Dynamics of the two states.
when we are saying that there's an isomorphism between states in this Hilbert space and that Hilbert space.
Yeah, everything is
They
similar.
evolve,
See,
right?
every quantity that you can compute in CFT must have its counterpart in ADS and vice versa.
Things like Hamiltonian.
Well, Hamiltonian, of course, is delta, right?
Yeah.
That, of course, matches. When you say that the spectrum is isomorphic, right?
Yeah.
That means all the eigenvalues of the Hamiltonians match. So Hamiltonians are manifest isomorphic between the two, right? But all correlation functions must also match, right? We check 2-point correlation function, but all correlation functions should also match.
Yeah. So states in ADS evolve the same way states in.
In CFT, exactly, because the Hamiltonian is the same, right?
Yeah.
Because they have the same energies. So as I said, every quantity in CFT must have its counterpart in ADS. So next time, which will be in March, right, we will start with a very specific quantity in CFT, and that is the entanglement entropy, right? In any quantum system, you can define entanglement. So CFT also has entanglement, right? We can identify some region in space, right? And we can say what is the entanglement entropy between the degrees of freedom inside that region and degrees of freedom outside that region. There must be a counterpart of that in ADS, right? And we will see what it is.